Greetings and welcome to another exciting lecture in geomorphology. We're concluding today our thoughts on geomorphic hydrology. So that's the goal for today. Um, Last video, we learned a little bit about how we do impedance probabilities and calculate kind of return intervals of different size events. We talked a little bit about how that can apply to both flooding or precipitation events. We're going to move on with our discussion of geomorphic hydrology, move out of the world of kind of just precipitation and think about once that water hits the surface. So the first part of our lecture is going to be talking about the hydrologic flow paths, the ways that the water moves across the surface and into the surface, and then how that water eventually gets to rivers. And that's going to be really important as we start to develop an understanding of how rivers work. We need to understand how quickly the water gets there and the way in which the water gets to the river. That's going to be really, really important today in the first part of the lecture. We're going to introduce a very, very important concept when talking about hydrology, and that's a hydrograph. A hydrograph is a way that we can quantify and understand the amount of water in a river over time. So that's a hydrograph. We'll be introducing that towards the latter part of the lecture, and then we're going to finish by looking at some spectacular landforms associated with water and water's flow at the surface and through the surface. Yes, you're right. We're going to be talking about karst, sinkholes, by the end of this lecture today. So buckle up, get ready, and let's dive into today's lecture. Okay, here we are, hydrologic flow paths. This is the first thing we're going to be talking about. We've already talked about water getting down to the surface. Now we're going to be talking about once the water's at the surface, how does it make its way all the way down to the river right here? Whoop, right there, the river right there. So that's what we're talking about here with these flow paths. Okay, let's see. Okay, the first flow path that's very, very important when understanding how rivers work is the concept of base flow. A base flow is the water in a river that is there even when it's not raining. So this only happens in perennial streams. Remember we talked about the difference between a dryland stream and ephemeral stream where there's only water in it when there's water flowing at the surface of the earth and dumping that water into the channel. A perennial stream is a river we have in more humid climates where there's groundwater flow that's contributing this base flow to the river. So right down here, looking low here, you can see the water table intersecting the surface of the earth. That's where we've got our river. Then the base flow, that groundwater flow, is kind of pushing into it continuously, pushing water into the river. Why is that? Well, we've learned a little bit about this already in our previous lecture when we talked about hydrologic head. And so the river is the low point in the landscape. And so because of that, hydrologic head is driving groundwater flow towards that low point and into the river itself. Okay, so that's base flow. The next hydrologic flow path associated with a rainfall event is going to be what we call Hortonian overland flow. Yes, Hortonian overland flow. And that's when it's raining so hard that it's raining harder than the infiltration rate. So our precipitation rate is greater than our infiltration rate, and that water pools up at the surface and flows over the surface. This is very, very common in regions where we don't have high infiltration rates, so places where we have lots and lots of bedrock and relatively thin soil. So again, arid regions. So here it is. Here's our picture, beautiful picture here of overland flow. Let's also watch a video here of overland flow. Okay, here we are. So this is a video that I pulled off YouTube, and what we're looking at is a rainstorm in Ocotillo, California. So this is in the Mojave Desert. So this is a classic location where one would expect Hortonian overland flow associated with a rainfall event. So here we're looking at a rainstorm, and notice that we're already seeing at the surface water pooling at the surface. So here our infiltration rate is low, and so the water is pooling at the surface and forming small little channels, and these channels start to run off. And so here we're looking at overland flow. Again, the soil is not completely saturated. It's just it can't soak in fast enough. And so we're watching that overland flow down and going onto a road right now. And so you can see several different places in the video where the water is flowing. Now the cool thing is because the pores aren't saturated, you're losing some of your Hortonian overland flow as it infiltrates down into the soil. Okay, as the storm progresses, you're collecting more and more water at the surface, and we're forming these small little channels at the surface. And in a rainstorm of this size, you generally are going to concentrate your flow into the low points in the landscape. And so you're not seeing flow over the entire surface. It's just happening in the low points. So you've got these what are called interfluves, which are the high points on the sides. And then the fluvial network is a little bit lower, and the water's collecting and running off down into those low points. All right, let's get back to the ground here. We got the bugs, but we're interested in the Hortonian overland flow. Ooh. And notice the front of this is very frothy and has a bunch of debris in it, which is really common in Hortonian overland flow. So did everyone see in the background there, the mountains in the background? That's really critical for developing this type of flow because the mountains are where you have very, very low rates of infiltration with all that bedrock. And so the water is pooling in the mountains and now it's flowing off over the surface. So remember, as I mentioned earlier, that it wouldn't necessarily even need to be raining right in this location. It's the rain in the mountains that's generating the overland flow that's now flowing down into the valley floor and on the bottom. So this is a nice picture showing in the bedrock up in the mountains where you're going to have low infiltration, right? There's going to be no infiltration on the bedrock, and so we generate lots of amounts of overland flow. Look how muddy that water is. That's all the suspended sediment we'll be learning about later in the semester in the water as it's flowing down. So this is look at all that bedrock. This is a great example of essentially zero infiltration, and so that water just runs off the surface and then is going to run down onto the alluvial valley floor down below where eventually it'll infiltrate into the ground. All right, let's head back to the video. All right, wasn't that a really, really cool video on overland flow? So that's Hortonian overland flow. Again, the cool thing about Hortonian overland flow is that sometimes you can get Hortonian overland flow in a region even if it's not raining there. So let's say it rains up in the mountains, and so you get a rainfall in the mountains, and mountains are full of bedrock, right? And so you exceed the infiltration rate, and then that water is flushed down the surface and down to the lowlands where you can get overland flow even if it's not raining down in the lowlands. Okay, let's move on to our next hydrologic flow path, and that's what we call right here, whoop, subsurface storm flow. So this is after it's rained at the surface and the water is infiltrated into the ground. We're going to have percolation of that water, and this is what we call kind of shallow storm flow. This is kind of relatively near the surface, and so the picture here is this is a huge pore, maybe associated with an animal burrowing. So we've got a big void space. The water can move through this big void space because it has a large porosity, and that hydrologic conductivity is going to be high. And so you can just put your cup right here and have the water pour right into it. That would be a what we call subsurface storm flow that eventually makes it down to the river. And then if we keep raining really, really hard for a long time, we can actually fully saturate the soil. And so when you get fully saturated soils, there's no void space left. So any excess precipitation at the surface, it has nowhere to go but run over the surface. We get what's called saturation excess overland flow. Does everyone see how that's a little bit different than Hortonian overland flow, right? Hortonian, you can still have voids in the ground that aren't filled with water. We just can't get the water down to them fast enough. Here, saturation excess, every pore is completely filled with water, and the water just pools at the surface. So this is common actually in humid regions where it rains a lot, and so you soak the ground's completely soaked, then there's nowhere left for that water to go. You've probably seen pictures or videos of large floods on the Mississippi River over the past several years. Most of that is due to excessive amounts of rainfall in the upper Midwest, where we've completely saturated the ground and we get saturation excess overland flow. And it's a way that we can generate really, really big floods. And we'll be talking about that a little later in the semester when we get to rivers and fluvial processes. So again, a time when you often see Hortonian overland flow would be in the springtime. So here we're looking up in Greensboro, Vermont. This is a picture from your textbook. Paul, one of your authors, has a house up here, which is why he's got this picture in the textbook. And we can see that the snow's melting here. We're coming out of winter. So all that snow melt has saturated the ground, and we end up with water running over the surface. So overland flow. Okay, now let's look at during a rainfall event, how that saturation excess overland, or excuse me, how all these hydrologic pathways connect and which ones turn on when during a storm event. So what we're going to be looking at here is a drainage basin. So here's the whole drainage basin right here. Okay, and we've got a river in the drainage basin. Then up here, we're going to be looking at time on the x-axis and looking at our basically precipitation amounts as little bars. So here we're at the start, there's not much rain, the storm kicks off. What we're going to be looking at, this is from your textbook, these are the different flow paths that are going to be flowing with greater flow going across on the x-axis, and then time we're going to have here on the y-axis. So when we first start our storm, when it first starts raining, maybe we just have that base flow. That's why we're not at zero. We have a little bit of base flow. Then we move through, and as it starts to rain, our first hydrologic pathway that's activated is that Hortonian overland flow. If that infiltration rate is low and water just starts running off the surface. So Hortonian overland flow starts first. As we start to saturate the soil, what kicks off next is our subsurface storm flow. So that starts to increase as well. And then notice here that also our base flow, because we're putting more water in the ground, our base flow rate actually starts to go up a little bit after our subsurface. So again, all these pathways are being activated as we move into the. All right, as we move a little more into the storm here, we've completely saturated the ground. And so what kicks off next is our saturation excess overland flow, which as we're having a very, very heavy rainfall event, that kind of takes over and is contributing water to the river. Notice here as well that we've got essentially the size of our drainage basin network increases over time. Does everyone see that? That as we start here, our river network, this is where there's water actually flowing in the rivers. It's just where we've got the base flow. Then as we move into that Hortonian overland flow, the smaller channels, what we call first order channels, start to get water in them. So our network of streams grows as the storm begins. And then once we get that saturation excess overland flow, then we've got the full drainage network with all of our streams flowing. Okay, whoops. And then eventually what happens is your storm starts to taper off and all these pathways will recede over time. All right. great. That gets us to this next really important concept, and that's the stream hydrograph. So a hydrograph is a way that we quantify the amount of water in a river over time. So on a hydrograph, you're going to have two axes. Your y-axis here is going to be the amount of water in the river, and we're going to be doing this in terms of volume per time. So oftentimes when we're talking about volume per time in rivers, we're either talking about cubic feet per second. So imagine a foot of water by foot of water by a foot of water, a cube, and three of the, so that in that a cubic foot per second would be one of those passing by you every second. So a cubic foot per second, but if you want to be in SI units and RSI, which we want to be, then we're not going to be talking about feet. We want to be talking about meters. So a cubic meter per second. Okay, so that's what we have on our y-axis here, cubic meters per second. Here's our river discharge. And then on the bottom here, our x-axis as we're going across, that's going to be time. We've thrown on here for some to help understand how a hydrograph changes time, the rainfall amounts. And so here, our y-axis, x-axis is still time. And what we're looking at on a secondary y-axis is the amount of precipitation. It's broken into discrete blocks, which is what we commonly see. This is the amount of rain that fell in, say, 10 minutes, then the next 10 minutes, and the next 10 minutes, okay? So here's what happens to a stream over time when it starts raining. We get the rain, then that water in the river starts to increase, and we get what's called the rising limb of the hydrograph. At some point when we're going to have the maximum amount of water in the river, we call this peak discharge. Then as we come down the other side, as it stops raining and we go down the other side here, that's the falling limb of the hydrograph. So we've got rising limb going down to falling limb. The peak of water in the river we call peak discharge. Okay. Some other terms we're going to have here that you should be aware of would be peak rainfall. So peak rainfall is the highest amount of precipitation during the storm. And then another term that's really important is what we call the center of mass of both rainfall and our discharge in our river. And so that's kind of the middle of the storm in terms of the total amount of water flowing in during that storm event. Okay, so here's our discharge right here. I also should note down here we've got our base flow. So our base flow, which goes up and then goes down. Okay, another term that is really important is our lag to peak time. So right here, lag to peak time, that's the time it takes from maximum precipitation to maximum peak discharge. So that's going to be in time units. That's what we call lag to peak. So depending on the storm, depending on the hydrologic pathways, different rivers and different storm events are going to have different lag to peak times. There's also another term here, the centroid lag time, and that's the difference between the center of mass of rainfall, center of mass of river flow. Okay, so that's it. That's kind of our basic hydrograph, and this is really common. We're going to be looking at lots and lots of hydrographs this semester, so get used to these. They're really useful. So in a geomorphology class, one of the cool things we can kind of ease out of this and start to explore is how the actual shape of the drainage basin, the morphology of the drainage basin is actually going to determine what the shape of the hydrograph is. Isn't that really cool? It's a concept that you don't necessarily think of. We think of rain, water goes up in a river, but actually how much it goes up and when it goes up is dependent on the basin. And so here we're looking at some differently shaped basins. So here we've got a drainage basin that is more it's a dendritic network that's kind of more what's the term I'm looking for here? More of a rounded drainage basin versus all the way over here. Yeah, right there, we've got our elongated drainage basin. And so what we're tracking here over time is what happens to the water in the river as it rains. And so here we're looking at the top here. This is a a we're looking at three different uh, gauges, three different places where we're quantifying the amount of water in the river during the course of a storm. A gauge that's very high in the river, a gauge that's a little bit lower where it's got a couple of tributaries that's come together, then a gauge that's just down at the outlet to the entire drainage. So when it starts raining, our first place where we're getting water is going to be right up in the mountains, and so we're going to see our peak first high in the mountains at these streams that are kind of these first order streams. That's where we're going to get our first peak. And then as that water flushes down through the stream network, we end up with a delayed pulse. And so in the larger basins, it takes a little time. And so as time goes on, we get a larger peak downstream, and then all the way at the bottom of the basin, we see our we see our greatest peak. And notice that the overall peak, so not just the timing, but the magnitude of the peak is greater. And that's because all the way down at the basin here, you've got all these tributaries that are contributing water to the stream. So, right, maybe I could try and draw that on there. See if this works. Nope. Nope. Can I get my tools up? All right, I'm not able right now to get my so there we go. Okay, sorry about that. Now we got our pen tool up. So again, notice here that our peak is greater and delayed as we move down the basin. Okay, so what I wanted to show was just what that is, why that number is bigger is because all these rivers, all these little tributaries are contributing water down to our river at the exit of the drainage basin. We can compare kind of the effects of basin slope and steepness and shape, excuse me, on a hydrograph as well. So in this elongated basin here, in an elongated basin, you might end up with a with water that gets to the main stem more quickly, and so we get a really big peak in these steeply elongated basins. Then as we start to kind of change these to a more gently sloped basin, we end up with not quite, we smooth out the hydrograph, and so we have the same amount of water in the river as under the curve here, but it's smoothed out because it takes more time for the water to get down to our exit here. So again, that shape of the drainage basin is really important in determining kind of what the floods look like downstream in their size. Okay, awesome. All right, let's look at an example of a large flood. That's exciting. So let's look at probably one of the biggest floods that the state of Vermont has ever seen. The 1927 flood happened in early November when we had heavy, heavy rain that saturated the ground. It was already wet conditions throughout all of October, and then we get this heavy rain, and we ended up with this massive flood that filled valley bottoms. So here's just kind of a graphic showing the cause of the flooding. It was a massive amount of rain, and so here we're looking at rainfall amounts in inches here. So in the center of the Green Mountains, we had over 6 inches of rain. That's over 8 inches of rain in the red there. So basically, there's all this water in the river, and there's nowhere else for the water to go. So it ends up in the valley bottom. And of course, that's a problem because oftentimes in mountainous terrain, humans, we put our cities at the bottom of the valley on the flat slopes, and so we end up with flooding in cities. Most of the bridges in Vermont are actually younger than 1927 because all the bridges were eroded away. Okay, let's add humans into the mix here. How do humans change floods and change the shape of the hydrograph? Well, they do it in several ways, but one really important one is this thing right here. What's this? Yeah, you got it, a parking lot. Why do parking lots change the shape of a hydrograph? Well, it's because a parking lot changes those hydrologic flow paths, how the water is going to get to the stream. So which one's going to increase? Think about that here. If you put a parking lot on the landscape, how is that changing the flow paths? Well, generally, most parking lots, what do you think their infiltration rate is? Yeah, you guessed it. Good. Yeah, it's 0. Most parking lots are impermeable. The water hits the surface and it runs off the surface. So which hydrologic flow path is going to go up? You guessed it. Yeah, it's going to be that Hortonian overland flow. And so all that water that used to soak into the ground and go down in those shallow subsurface flow paths, all of a sudden, all that water is at the surface and it runs right off the surface, and you end up with huge floods. So humans change the shape of a hydrograph. We call this an urbanized hydrograph or an urbanized flood. And so what do we see? We see urbanized floods generally have a greater peak discharge, and you see a shorter lag time. And that's because all the water is immediately going down into the channel. So look at this here. This is under natural conditions, what our hydrograph would do. Whoop. But now, because we've activated only essentially the Hortonian overland flow paths, all that water goes into the stream really quickly. And this can be a huge problem, right? When we've designed where our cities are, when we design our infrastructure, we kind of designed that with this in mind. But now all of a sudden you get these peakier floods. So we often see that as we build in a landscape, those floods become more damaging because we're putting buildings there that can get damaged, but we're also changing the shape of the hydrograph. And so because of that, you're going to see essentially more flooding. We're going to see water higher up on the floodplain because of this urbanization effect. So let's look at this again. We're going to look at this extreme event from Hurricane Harvey that we've already mentioned several times in this class, but it's a good one. So let's watch this.
Hurricane Harvey is a record-breaking storm. It's the most extreme rain event in Texas history. But the city of Houston has some unique geographic and design challenges that have contributed to the flooding disaster. Greater Houston is situated on a flat plain near the Gulf of Mexico and sprawls over an enormous geographic area of 8,260 square miles. It's so massive you would be able to fit the cities of Washington, D.C., Chicago, New York City, and San Francisco well inside Greater Houston's borders. Why is it so large? That's partly due to explosive population growth. From 2000 to 2010, the Houston metro area swelled to 5.95 million people, a 26% increase. Houston famously has almost no zoning codes, meaning there is no strict regulation of what type of building can be built and where. Research has found that less restrictive zoning practices that encourage low population density, like Houston's, can keep housing prices low, but they can also contribute to what's called urban sprawl. That means more buildings, more parking lots, more roads, generally more concrete, which is impervious to rainfall. In the past, rainfall in the Houston area has been drained away by a series of bayous and water-absorbing prairie land. As urban sprawl crept outwards from the city center, development gobbled up wetlands, trading absorbent prairie grasses for new construction. Although Houston sits on a flat plain, it's far enough above sea level that storm surge really isn't the biggest worry during a hurricane. Rainfall and rainwater runoff is the real problem. Houston has consistently been upgrading its flood preparedness for decades, but a larger question remains on whether those flood preparations have been able to keep pace with the city's growth. In Houston, stormwater management has been about directing rainwater runoff away from homes and businesses. Roads are part of that runoff plan. Those photos and videos you saw of flooded out highways, they look catastrophic, but they're actually working exactly the way they're intended to, channeling floodwaters away from homes. That's one of the reasons why Houston wasn't evacuated before Harvey. Having thousands of people stuck in traffic on those roads while waters rose would have been truly catastrophic. At the same time, development of homes and businesses has continued in the 100-year floodplain areas within the city itself. But scientists worry that even the maps that designate 100 or 500-year floodplains might be outdated as climate change continues to increase the frequency and severity of storms. The terms 100-year and 500-year flood don't mean that a flood will happen in an area once in 100 years or once in 500 years. It means that areas in a 100-year floodplain have a 1% chance of flooding every year. 500-year floodplains have a 0.2% chance of flooding every year. The flooding due to Hurricane Harvey in 2017 was the third 500-year flooding event in 3 years. Either Houston is incredibly unlucky, or there's a higher chance of catastrophic yearly flooding in Houston than 0.2%. While infrastructure is built to direct water away from homes, so much rain fell during Hurricane Harvey.
Okay, excellent. Hopefully that worked. Okay, and so again, this brings us back to this this issue here of recurrence intervals, right? We talked about recurrence intervals, and Houston had its third 500-year flood in 3 years. Well, how is that possible? Well, again, remember that the past is not necessarily the best predictor of the future. We've got climate change, but also we've got a change to the hydrograph, right? All of a sudden, we've put all these buildings on the landscape, and so our hydrographs are peakier. And so in this case, the past is a terrible predictor of the future. Okay, so this is actually a really common, sorry, looking at my slide here, a really common avenue or job that a lot of people in hydrologic fields get into is trying to predict floods. And so we'll build things like weirs so that we can quantify the amount of water in the river, calculate those hydrographs, and we are trying essentially to then use this as a weather station, and we can actually start to estimate the size of floods. So that's a really important field, is the ability to predict flooding. Okay, and so kind of our last thing here, I just wanted to show you again what scientists are doing with this is that, like, you know, after big flooding events like Hurricane Irma here, we're looking at ways that we can improve our weather forecasting. How can we do a better job of predicting the size of these floods so that we can help people to evacuate people when they need to be evacuated, and maybe have a reasonable building design for buildings that can withstand floods as well, or potentially even have different zoning laws that determine where people can build based on how floods are changing as humans urbanize a landscape. All right, excellent. Now that we've gone through that, let's finish off here with the cool stuff, the hydrologic landforms. So let's talk about some spectacular features associated with water moving through the surface of the earth. This is generally the field of karst. So when we're talking about karst, we're talking about the dissolution of rock, generally limestone, but it could be marble, dolomite, anything that's easily dissolved, all right? Go back to your chemical weathering lecture and we can think about which rocks dissolve really easily. It's mostly limestone. So where we have limestone and water moving through that limestone, we dissolve away that limestone and we end up developing these subsurface caves that grow in size over time. We have these conduits. We can have conduits that link our caves together. And what happens when you connect those caves to the surface, you can no longer support the ground on top and the cave collapses and we end up with a sinkhole. Oftentimes, kind of like a sinkhole where we just have a connection between the surface and the subsurface, we'll end up with springs in our karst landscape as well. Okay, so that's kind of our karst topography. Let's look at what this looks like in terms of what a topographic map looks like. And what I'm going to draw your attention to are in karst landscapes, you end up with all these little depressions, right? These little depressions in the landscape. So that's what we're showing here. All these pictures are showing these kind of high points and low points associated with these depressions associated with a sinkhole. Now, everyone look at this one right here. Kind of squint in on the screen. Does everyone see there's the little hash marks? Oh, our camera turned off. Sorry, hold on. Okay, we're back. Sorry about that. Okay, so keep looking right in here. Does everyone see this circle I've drawn? And look at those topo lines in detail. What do you see? Kind of squint in there. There's those little hatch marks on the topo lines, right? That's telling you that you've got a circular depression, right? How do you tell the difference between a hill and a depression on a topo map? When you've got circular topo lines, but they're going down in a depression, we put the hatch marks on them. So that's what we're showing here are these sinkholes where we have these depressions. Okay, so this is a classic topographic map right here from a karst landscape. All right, here's a picture of one of these sinkholes. These can be really dangerous because we don't necessarily know where they are. So you'll often see in places like Florida, you'll have buildings or cars, the street will just collapse and the car or the building will fall into the sinkhole. Okay, another spectacular landform associated with karst is what we call tower karst. The tower karst are these mountains. Everyone see these just mountains associated with dissolution of limestone in karst processes. Just make these spectacular landscapes associated with karst. And how this works is essentially this is when you've got lots and lots of limestone that is eroding away and dissolving away, and the landscape's lowering over time. So we're talking about processes active over millions of years, and what happens is for whatever reason you have joints or some sort of fractures, faults or something in the bedrock that are in between your mountains, and so that's where you can concentrate your dissolution, and maybe the mountains themselves aren't quite as don't have as many fractures in them, and so they end up starting as high points in the landscape. And so this is kind of a positive feedback loop that as we start to lower the landscape, these mountains are high, and so you end up water flows out of them, groundwater flows out of them, and you can't do as much dissolution because the ground down here is where you're going to have saturated ground all the time where you can dissolve more limestone. So they kind of emerge from the landscape as it lowers over time. So let's look at that in schematic here. Again, we start with just maybe a more fractured zone in the limestone right here. Right? And so as we start to lower the surface, we're going to concentrate that weathering because hydraulic head is going to force more water into the low points in the landscape. And what happens is our towers emerge over time. And so this is how you can start with a flat ground and you end up with these tower karst. Isn't that cool? We call that tower karst. Okay, we can get what's called drip landforms, and these happen within caves that when you have water that's rich in dissolved calcium, we can precipitate out that calcium in the cave. So you can make spectacular stalactites, which are the ones that hang down. And so that would be groundwater that's flowing down this surface here. And then you concentrate the water at the tip of it, and then the carbonate precipitates out, and you grow these things down. We call that a stalactite. And when they're growing from the bottom up, here where you've got a drip and that water's dripping on the ground and you're building up, we call that a stalagmite. Okay, another really cool landform is what we call tufa. And tufa is where you have springs that are rich in calcium, kind of emerging at the surface, and you basically, as you kind of release these at the surface, you precipitate out the calcite and make tufa. You can even do this underwater, and so where you have high lake levels, so this would have been a higher lake in the past, and then we had springs under the lake, and so you build these tufa towers in the lake, and then once we lower the lake level, these towers of tufa emerge. Okay, that's all I've got for you today on hydrologic landforms. So thank you all for watching. Pretty cool stuff, isn't it? So enjoy it. Go take a look, take a spin around Google Earth and find some of these tower karst landforms. They're pretty spectacular. All right, have a great day. We'll see you later.